Welcome to Unit 9, Lesson 4 on mirrors. Incident rays and reflected rays make equal angles with a line perpendicular to the surface, called the normal, which is also known as the law of reflection. We've talked about that with waves for the last few days. So remember, the angle of incidence is going to equal this angle of reflection. Taking a look at the example below, this is a plane mirror and an object and the image being seen through the eyes of someone over onto the left side of this mirror here. So if your eye was over here, let's look at the light rays that are involved here. So if we have an object, in this case it's a tree, and we look at just two light rays of many that would be leaving this object. Let's look at the top ray here. You'll see that it will travel parallel to this principal axis here. So it'll hit the mirror at 90 degrees and therefore reflect exactly the same amount back at 90 degrees, so straight back. If you look at the next ray here, you'll see that that law of reflection is followed here. So the angle of incidence here, this top angle here, will equal the angle of reflection over there. Now those light rays, when they come back into your eye over here, those light rays will appear to have come together on the far side of the mirror over here. That's why your eyes pick up the image behind a mirror that looks the same height as the actual object. It's the same distance behind the mirror as the object is in front of the mirror, and therefore it looks exactly the same. So a couple things to notice is that these light rays here are diverging from each other. In other words, they're splitting apart. What you see is the image behind the mirror. In this case, that image is a virtual image because the light does not actually start there. It only appears to come from there. Your eye can't tell the difference between an object and its virtual image because the light that enters your eye enters exactly the same way as if the mirror wasn't there at all. So a virtual image is the same distance to the mirror as the object is, and it is obviously the same size. So the question is, if you have a blue shirt on and you look at it in the mirror, what color is the image? And what does that tell you about the frequency of the light that's reflected from the mirror? And if you take a picture of yourself in front of a mirror, if you're standing 2 meters in front of the plane mirror, at what distance should the focal length be set at so that your image is in focus? So the answers to those questions is that the color of your shirt will still remain blue, and that's because the frequency of the light is not changed when it is reflected. You should also set the focal length of your camera to be 4 meters. It's 2 meters that you are standing in front of the mirror, and your image will be 2 meters behind the mirror, and therefore your total distance away should be 4. There are two types of images in the mirrors and lenses that we'll talk about. You need to be able to identify which type of image is being formed in each scenario. So real images are formed by converging light rays, and that means that the light rays are coming together. So anytime an image is being formed where you see the light rays coming together, you know that's going to be a real image. And anytime you see that light rays are spreading apart, like we just saw in the last example of a plane mirror, diverging light rays are spreading apart and therefore form a virtual image. Virtual images cannot be projected onto a screen, like a movie screen, and therefore it's just your eyes picking up the image as though it appears the light is coming from there. The first type of shaped mirror we'll look at is a concave mirror. So that's where we're looking at the bowl-shaped side of the mirror there. So some points of interest that you need to be aware of when we talk about a ray diagram or a mirror and lens diagram. Point C is the center of the mirror. So that means if we took this mirror and we made a complete circle around here, that would be the exact center. So the distance from the center to the mirror is the same as the radius of a circle. Next point is the principal axis. The principal axis is just this center line that we draw through straight through the mirror or the lens. Point P is the center of the mirror that axis is running through, and F is the focal point or the focal length, and that's an important point that we'll see down here. Focal lengths are always half the distance to the center. So for example, if I tell you that the center of curvature is 20 centimeters, that would be a distance of 20 centimeters from there to there. And then you would have to know that the focal length is exactly half that, so that would be a focal length of 10 centimeters. In this section, we're going to learn about the concave mirror ray diagram rules and how they will help us find an image being formed. So the three rules in this box here need to be committed to memory, and then you need to be able to implement them on paper with a ruler and a pencil, and then help find the image. So the first rule here I'll do in this picture here, these arrows should be actually connected to the principal axis. And the generic version of any object that we're talking about is represented by an arrowhead. So we label that as an O for the object. Next, you're going to want to grab a ruler, and then we're going to follow these rules as they're indicating here. So incident rays parallel to the principal axis are reflected through the focal point. So I'm going to grab my ruler and line it up parallel with the axis, and I'm going to take my pen or pencil, and I'm going to go parallel to the axis. And again, accuracy counts. You can see that that line wasn't very parallel. So we'll try again. So we go parallel to the axis. And then once we hit that mirror, it follows the law of reflection, so that if you think about being perpendicular to that surface there, the rules are that it will reflect straight through that focal point. Again, I missed it a little bit, but hopefully you get the idea. So parallel to the axis through the focal point, and then the next picture here we'll look at rule number 2, that light rays that go through the focal point will reflect parallel to the axis. So through the focal point, and then again following the law of reflection, will reflect parallel to the axis. The third rule is that any light ray traveling through the center of the curvature will hit the mirror and reflect straight back, and that's because that's the only situation where that light ray is hitting the mirror at 90 degrees. So it'll be traveling towards the mirror and then reflecting straight back. Your job is to use all three of these rules on a ray diagram, and anytime you see that two of the lines are intersecting with each other, that tells you where the image is being formed. So a big point of these three rules that only two of those three rules need to be satisfied. The mirror and magnification equations are found in these two boxes here, and they help us calculate exactly where the focal length or the distance of the image or the distance of the object are. So these equations back up the ray diagrams. They basically are telling you the mathematical answers to the diagrams that you should be solving. So we're going to use both the rules for our diagrams to find the image on our page in a drawing, and we're also going to calculate it. So a couple letters that you need to be aware of there. Remember, F is the focal length. So again, these are distance measurements. DI is distance to the image. DO is distance to the object. HI is height of the image. And HO is height of the object. M stands for magnification, and if you think about what that means, if I tell you that something is 5 times magnified, it means that the height of the image that you're seeing is 5 times larger than the height of the object. So we'll practice using these equations when we start to use the ray diagram to find images in the worked examples. The values for positive and negatives, we'll talk a bit more about that, and you'll see those when we start to calculate those values in our worked examples. Concave mirrors can form virtual images in one situation, and that is where the object is inside the focal length. So these types of mirrors are typically found in makeup kits if someone wants to see an enlarged image of their face. And so what's happening is the light rays are diverging off of the mirror, and therefore your eye, which would be on this side over here, would see that that light would appear to be coming together, forming an image on the far side of the mirror. Notice that that image is going to be larger than the object. It is still in the upright position, but it's a virtual image because the light rays again are diverging into your eye. The other type of curved mirror that we'll look at is a convex mirror, and that's a mirror that you'll typically see on side view mirrors of cars or trucks. You'll also see them in the corners of convenience stores, because what they do is allow for a wide field of view. So if we look at the object here represented by the arrow, we're still following the same rules that we talked about before. We go parallel to the axis, and then we line up our ruler so that it would be lined up with the focal point. Those dashed lines are not actual light rays, because light does not go through a mirror, it will be reflected. So those rays will be reflected in that direction with your ruler lined up. The next line that you're going to draw is line up with the center of the curvature of the mirror, and you'll see that those rays are perpendicular to the surface of the mirror and will reflect straight back. Where those two lines appear to come together, that's where the image will be formed.